Hello everyone. In last class we discussed transient response of series RLC circuit with AC excitation. So that is a last topic in the first part of the second unit. So in second unit we have the two different parts: transient and steady state analysis of RLRC RLC circuits, and another one is resonance concept. So in this class we are going to discuss what is resonance, what is the need of the resonance, series and parallel resonance circuits, and how can you calculate the bandwidth and quality factor for the given resonance circuit. So in many electrical circuit, if you observe, resonance is very important concept, very important phenomenon. So that's why we have to study this resonance. Why? Because it will be very useful, particularly in the field of communication and in so many areas. For example, the radio receiver has ability to select the desired frequency, let us assume, transmitted by the station. So the radio receiver rejects all other unwanted frequencies transmitted by other stations. So such selection of required frequency and rejection of unwanted frequencies is really based on the concept. The principle is called as a resonance. Means, how can you define the resonance? Means, in general, the resonance is defined as a phenomenon where the applied voltage and current both are in phase. This is the one more concept. What is the meaning of in phase? Means the phase angle between voltage and current is either 0 degrees or 360 degrees. In other words, an AC circuit is said to be in resonance if it exhibits unit power factor. Unit power factor means the power factor formula is cos pi. Unit power factor means it should become 1. So when will we get this one? Whenever pi angle is 0. So this is another way we can define. That means applied voltage and current results in the resulting in the in phase. So in AC circuit, under the conditions of resonance, the reactance gets cancelled. Means if you take the inductor reactance and capacitor reactance XC, both gets cancelled, then the circuit will become simply resistance. So that's why where current and voltage are in phase. So now we have to discuss one important parameter or factor of this resonance circuit, that is called as a quality factor, or we can say figure of merit. So the resonance is observed in the AC circuit consisting some reactive elements like inductors and capacitors. So these two elements are basic passive elements of energy storage devices. We know that. So it is found very convenient to express what is the efficiency with which these energies can be stored in these elements. So that can be defined one factor, or that can be measured by one factor. That factor is called as a quality factor. So what exactly quality factor determines here? What is the how efficiently these inductors and capacitors can store the energy in their elements. So now let us take down this quality factor mathematical equation. Quality factor Q equal to 2 pi into maximum energy stored per cycle divided by energy dissipated per cycle. This is the mathematical formula we are using to find the quality factor of either series RL or RC circuit. Okay, now let us derive the expressions of the quality factors for inductors and capacitors. Okay, now I am taking the first derivation of the quality factor for inductor. Now I am assuming one in series RL circuit and excited with AC voltage source V, and let us assume the current I is passing through the circuit. Consider the sinusoidal voltage V is applied to an inductor and with leakage resistance of a R. So what is the maximum energy stored per cycle is 1 by L2 into L into Im whole square. Im is the peak maximum value of the current in the circuit. What is the average power dissipated by the inductor is Im by root 2 whole square, I square into R formula, but here we are considering RMS value, that's why it will become Im by root 2, 1 by 2 Im square into R. So what is the total energy dissipated per cycle? Energy dissipated per cycle is given by P by F, that is equal to, per cycle means we are taking the frequency parameter, 1 by 2 into Im square into R by F. Now if you substitute these terms in the quality factor, Q equal to 2 pi into maximum energy stored 1 by 2 into L into Im square, power dissipated per the cycle 1 by 2 into Im square into R by F. So if you solve these two equations, this numerator and denominator, we will get 2 pi F into L by R. So we will get Q equal to omega L by R. The quality factor of the series, that inductor circuit is omega L by R. And now let us consider what is the quality factor of the capacitor, another energy storage element. Now consider the same sinusoidal voltage V is applied to the capacitor with the series leakage resistance of R, and current I is passing through the circuit, let us assume. So what is the maximum energy stored by the capacitor? Omega C equal to, we know that, of C V square, but in the place of V we are taking V suffix M, that is maximum voltage or peak voltage, and 1 by 2 into C into, in the place of V I am substituting something current, in terms of currents we are deriving, that's why we will get 1 by 2 into Im square by omega square into C, where V equal to I by R, I into R, where X equal to 1 by omega C, that term we are using here. So what is the power dissipated, average power dissipated per cycle in the capacitor equal to Im square by root 2 into R, that is equal to 1 by 2 into Im square into R. But we have to take this one per cycle, that's why we have to divide this total equation with frequency. Now substitute these terms in the quality factor mathematical equation. So Q equal to 2 pi into maximum energy stored Im square by omega square by C, maximum power dissipated by F. So if you solve this equation, we will get the quality factor equal to 1 by omega RC. These two are very very important formulas. In further classes we are going to use these two formulas. The quality factor of the inductor is omega L by R, where the capacitor is 1 by omega RC. So what actually quality factor indicates? How effectively these two elements can store the energy in their formats. So when the quality factor of the resonant circuit is given, we can find the frequency of that circuit.